So the last lecture was the beginning of a transition from the electrostatics portion of the course to the magnetics portion of the course. And the way we did that was we established the idea that current or moving electrical charge will sometimes be established when there are electric fields, depending on the material. And so starting here, we're going to consider the impacts of those currents, namely that it establishes magnetic fields, which will in turn exert forces back onto moving charges. So this lecture is divided up into 4 segments. The first is the Biot-savart law, which will be the most basic way to define how magnetic fields and currents relate to each other. Then we're going to cover Ampere's law, which is another more general way to do that. Next, permeability, which is the magnetic equivalent of permittivity. It's the material properties of how a material responds to magnetic fields. And finally, we'll talk about magnetic boundary conditions and compare them a little bit to electrical boundary conditions. So before we get too far into segment 1, which is the Biot-savart law, I want to kind of give you a preview of everything that we're going to be covering with regard to magnetic fields. And so this is sort of intended to draw some analogies between electric fields and magnetic fields, since there is a lot of parallels between them in the way they are set up. And these equations here are split up into 2 columns, electric fields and magnetic fields. And I should emphasize everything here is what we're going to call static, which means nothing is changing with time. The time derivative of any quantity equals 0. And so let's review the electric field laws and sort of take a look at the equivalent of the magnetic fields that we're going to come up with. So for electric fields, we started out with Gauss's law. Gauss's law told us that the surface integral of this electric flux density D around any closed surface in the closest volume is going to be equal to the total charge that's within that volume, or the sum of all the charge densities that are within it. The equivalent for magnetic field, instead of the electric flux density D, we're going to have a magnetic flux density, which is B. And if we take that same integral of B around the surface, that's going to equal to 0. The reason it's equal to 0 is because there's no magnetic charge. And so effectively, it's almost like the Q is 0 for anything that's magnetic. Right, so this law right here is sort of the parallel for magnetic fields. Let's keep going. Gauss's law in the differential form was that the divergence of the electric flux density equals the charge density, and it's the same for magnetic flux density, except we just have a 0 because there's no such thing as magnetic charge. These next 2 are what we're going to call Ampere's law. Whoops. These next 2 here are what we're going to call Ampere's law. This is going to be our first way to relate magnetic fields to currents. And it's going to tell us that if we take the loop integral of the H, and the H is the magnetic field, which is separate from the magnetic flux density, and take the integral around the loop, that will equal to the total current that is enclosed by that loop. And that's going to be called Ampere's law. The equivalent of that for electric fields was that if we take the loop of an electric field around a path that encloses a surface, that equals to 0. That was the way we sort of defined the idea of voltage. That if you define your altitude and you walk around and meander and come back to where you started, you're at the same altitude where you started. So for magnetic fields, it's actually not true. In fact, if you take that loop of a magnetic field, H, you get the current that's enclosed within that loop. In differential form, that was the same as saying that the curl of the electric field is always equal to 0 for static cases. And for magnetic fields, the curl of the magnetic fields equals J. That the swirliness of magnetic fields around a location is directly proportional to the amount of current that's passing through that particular location. All right. So you can already see that there are some analogies that are being drawn right here. Remember also that this is electrical current on the right here. Because there's no magnetic charge, it also means there's no such thing as magnetic current, which is why for electric field, this quantity right here equals to 0, right? The curl of B equals 0. So everything is kind of working. The parallels between electric fields and magnetic fields, the only big difference being that there's no such thing as magnetic charge, and therefore no such thing as magnetic current. And these parallels are going to continue when we look at the boundary conditions. The boundary conditions are, we had 2 of them for electric fields, which is that the normal vector n, which was a vector that points into medium 1 and perpendicular to the surface, dotted with the difference of the electric flux density on both sides equals the surface charge that's built up along the surface. For magnetic fields, we're basically going to take the d, the electric flux density, and swap it with b, which is the magnetic flux density. And on the other side, because there's no magnetic charge, we're going to set that equal to 0. For magnetic fields, we're going to take this n vector and cross it with the difference of the magnetic field on both sides of the boundary. And that's going to equal to the surface current that is flowing along the boundary. And that's precisely analogous to the same thing except with electric field. But because there's no such thing as magnetic current, this term right here is going to be equal to 0. So again, the duality between electric fields and magnetic fields are continuing. All right, the next panel, this is where we define magnetic and electric fields. So we had D equals epsilon E. There's a relationship between the electric flux density and the field, or the flow of field lines compared to the forces. And the relationship there is this epsilon, this permittivity factor that connects them. And you could also write the permittivity as some scalar multiplier times the value of the free space value. And the same is going to be true for magnetic fields. We're going to have B, the magnetic flux density, defined as mu, what we're going to call the permeability times the magnetic field H. And the permeability can be written as a static multiplier mu r times the value of free space. And again, D and E are electric flux density and electric field in coulombs per meter squared and volts per meter, and equivalent units for magnetic field is the magnetic flux density B is Webers per meter. That's W-E-B-E-R, but pronounced typically Webers. Now, there's no such thing as magnetic charge, but it turns out that if there were magnetic charge, we know what the units would be. It's a Weber. So this is actually the equivalent of coulombs, except for magnetic charges, which again don't exist. For electric field, it's volts per meter. And in magnetic field, it's amps per meter. So amps is kind of like the magnetic analogy of volts. And we'll see that in later contexts as well. That should make some sense from transmission lines as well, because voltage and current were the two things that created each other. So if we're building up to the idea that electric fields are going to create magnetic fields and vice versa, we should see volt and an amp kind of swapping between the two, and that's what's happening. The last thing I want to highlight, I'm going to skip this fields and potentials right here, but the last thing I want to highlight is the energy storage. And for electric fields, we have this concept of capacitance, that if you have two conductors that are storing some amount of charge and you have a voltage difference between them, the energy stored is going to be equal to 1/2 times CV squared, where V is the voltage and C is the capacitance. And for inductance, the equivalent concept is going to be, for magnetic fields, the equivalent concept is called inductance. And it turns out that the energy stored by an inductor is 1/2 times Li squared, which kind of makes sense. Capacitor is kind of like the equivalent of inductor and vice versa. And current is the equivalent for voltage. And if you look at the energy that's stored in fields, in electric fields, it was 1/2 times epsilon times E squared. And for magnetic fields, it's 1/2 times mu, the permeability, times H squared. So there's a duality there, a parallel between electric fields and magnetic fields, as long as we swap voltages for currents and currents for voltages. We swap electric charge for magnetic charge. And we swap permeability for permittivity. We swap mu for epsilon. All right, so let's talk a little bit more about electric fields and how they come about. All right, so the fundamentals of magnetic fields come from the following. If I have a magnetic field, and I'm going to draw these dots right here to indicate that the magnetic field is coming out of the page. And we're going to describe magnetic field as having a vector B that's coming out of the page. And let's say I have a charge plus Q, and it's moving in this direction with velocity V. Then there is a force exerted on that charge, which is going to be equal to the value of that charge Q times the velocity V crossed with the magnetic field. In this case, that cross product, QV cross B, if you take the right-hand rule, sweep the V into the vectors coming out of the page, you end up with a force that's going to be this way. Wait, sorry, no, I got that backwards. You're going to end up with a force that is downwards. So what actually ends up happening is you're going to get circular motion. This charge right here is going to move in a circle because the force is always perpendicular to the velocity. If it were a negative charge, by the way, if this were a negative charge and we're moving this way, then you get a force going the other direction here. And so you get circular motion that looks like that. All right. What's important about this is that the force is always perpendicular to the velocity, which means that the energy of this moving particle can never change, only its direction can change. This formulation comes about from the observation that if we have two wires and we have a current along both those wires, then you can observe, and this has been done, that there is an inward force that draws those two wires together. And the way to explain that was through this concept that you have magnetic fields. The first wire establishes a magnetic field, which then exerts a force on the moving charges in the second wire, and vice versa. And this force right here, QV cross B, is the way that we sort of first think of the magnetic field. This is called this is known as the Lorentz force. All right. Now, more generally, the way that fields relate to currents is with something called the Biot-savart law. The Biot-savart law is basically the magnetic field equivalent of Coulomb's law. It's going to help us take little pieces of current and construct what the total magnetic field is. And it looks like this. The magnetic flux density B, right? And again, this is magnetic flux density. Has units of Webers per meter squared. Weber, again, is the unit of magnetic charge, if there were such a thing as magnetic charge. It turns out to be equal to mu, the permeability of the material, divided by 4 pi, times integral of the current times small lengths cross with r minus r prime divided by an r minus r prime cubed. Now let me remind you what this is. All right, IDL basically represents a very small segment of current where we have a little bit of a current and a small length, right? So DL basically points in the direction of that current, and I is the current that is running along. So if we have a long wire, for example, and here is the current along that wire, this would represent one small piece of that wire. And this term right here is the contribution of one small piece of the wire, right? One tiny piece of the wire that is carrying current, right? Where I is the current along that wire and DL is just a small segment along it. And the integral is going to sum up all those contributions. All right, now let's say we want to figure out what the magnetic field is here. Okay, this is our observation point. And our origin will be here. Okay, this is our origin. All right, so the vector r prime is going to be a vector that points from the origin. Oops. Will be a vector that points from the origin to the source or the segment of current. That's going to be r prime. The vector r is going to point from the origin to the observation point, in which case there is another vector that goes from the source to the observation point, and that will turn out to be equal to r minus r prime. And so that's what this vector right here is. This r minus r prime. This is a vector from the source to the observation point, or the place where we want to calculate the magnetic field. All right, and this contribution on the bottom, this is our equivalent of r cubed. It's the length of this green vector here cubed. And this is really a 1 over r squared term, because this upper term right here, this r minus r prime, has a length to it. And so if we want to make it 1 over r squared, we have to cancel out that length and then put in another r squared term. So that's why this is a cubed right here on the bottom. All right. Now this magnetic flux density B is going to be related to magnetic field in the following way. There is mu times H. H is what we're going to call the magnetic field. Okay, this is magnetic field. And it's going to have units of amps per meter. And mu again is called the permeability. It tells us the way in which a certain material responds if a magnetic field is applied to it. Mu can also be written as some relative value times the free space value, where the free space value is 4 pi times 10 to the minus 7 henries per meter. Henries, by the way, is the unit of inductance. All right. So bear in mind, there is this cross product right here between the dl and the r minus r prime, which means that if I'm considering this configuration right here, I've got the dl vector is pointed in the direction of current, and r minus r prime is pointed this way. So the magnetic field is going to be pointed in and out of the page, right? It's going to be pointed perpendicular both to this r minus r prime vector and to the current. So in this case, it ends up pointing, in the direction through the page. So magnetic fields are perpendicular both to the current sources and to the direction that an object is from the magnetic field. All right. Now this is sort of the magnetic equivalent of Coulomb's law. It's a way to take some distribution of current and immediately calculate what the magnetic fields are from that, right? Or really magnetic flux density from which we can get magnetic fields. Now, much like Coulomb's law, there are a number of configurations for which you can analytically solve this. And there's a very small number of them because you can't sort of solve any arbitrary problem. Outside of your basic physics class, you really don't need to know how to do this, how to actually set up and solve triple integrals analytically, or double integrals, or whatever it is. Now, in the notes, I do have 4 different examples of cases where we can solve the magnetic field. You can find these in most physics textbooks. For example, the magnetic field from a wire segment that has current along its I. And your observation point is over here. And from whatever this observation point is, you can define these 2 angles here. This angle is theta 1, and this angle is theta 2. This line right here, let me put that in blue. This dashed blue line over here is going to be perpendicular to the line segment itself. We can figure out what the magnetic field is from that, and it turns out to be B equals mu naught I over 4 pi s, I'll define s in a second because I forgot to, times sine of theta 2 minus sine of theta 1 in the z direction, so it means it's coming out of the page. S, by the way, is this length right here, right? The perpendicular distance from the current segment to your observation point. That length is S. All right. If the wire is infinite, then this simplifies to B equals mu naught I over 2 pi s for an infinite wire. Because what happens for an infinite wire is theta 2 becomes positive 90 degrees and theta 1 becomes negative 90 degrees. And so you end up with this. Now, this is one example. In the notes, there are 3 more. I'm not going to go through it. In this course, I'm not expecting you to learn how to solve double and triple integrals analytically because, again, there's a very small number of cases for which you might actually do it. But it is important that you be able to do this numerically. And so you can still set this up with the computer. This Biot-savart law integral right here. You can still set this up with the computer and discretize space. So take your wire or take your current source, divide it up into very small pieces, and figure out the contribution of each one of those, take that cross product, and just add those up with a big sum. And that's the way you can do this numerically, even for arbitrary configurations. This blue dashed line that I've drawn here is not a neat, easy function that I can take integrals of. But again, you can do this with computer in small pieces. All right, so I'm going to leave it there as far as the Biot-savart law goes. But as we talked about with electric fields, Coulomb's law was very limited in that it was only sort of useful for a small number of scenarios. And a more general law that we used to relate fields to charges, we call that Gauss's law. In the next section, Ampere's law, we're going to talk about the sort of magnetic field equivalent of that.